Good afternoon, everyone. Uh, this is Nagraj, um, and today we're going to discuss about the Microstrip parallel coupled bandpass filter design on at 2.4 gigahertz. So basically, I wanted to discuss like how can we design a parallel edge coupled bandpass filter on the HFSS software. On the internet, I found this paper. So this is, I think, the communications for applied electronics one. So this one I'll try to design in the HFSS software, and let's see. Okay, currently I go deep into the theoretical concept like the resonating frequency, fractional bandwidth, and the inductance and coupling coefficients, and LP and CP, the shunt capacitance, series capacitance, and these are the conductance. These are the mutual conductance, and we have even mode impedance and the odd mode impedances. I think you have to have an idea about what all these, and once you have all the idea about all these parameters, you will end up with the tabular column of even mode and odd mode impedances. And once you dump this even mode and odd mode impedances in the microstrip, any couple line layout and structure, you'll get the length, width, and spacing between them for the couple line structure. So if you get these length, width, and spacing as tabular column, it is good enough to design the bandpass filter. And you have to understand what is the substrate you're trying to design. As the author has decided to go for the dielectric substrate dielectric constant of ER 4.4, that means FR4, 1.6 mm, conductor thickness and frequency 2.4 gigahertz. We choose all these things, and don't without wasting time, we'll directly go into the design part. So first, I think if you are ready enough, so we'll try to design a new um, ADT file. Okay, a new design. I'll name it as the edge coupled edge coupled VVF. Oh, okay. Now I'll try to first give. I'll create a substrate. So I'll give the substrate length. For suppose length, I'll just now give as 20 mm, and width 20 mm again, and height is h and 1.6 mm. So uh, then I'll create into top. So let's see. So now I think I've created this much. So once the I've created the substrate and all those things, so now I'll go through the first parallel coupled line. So the distance between the corner to edge, that's up to our wish. But let's focus on the spacing 0.6, 1.7, and 2, and 1.7, 0.6, 0.6, 0.6 is 1, and 1 is 1.7, 1.3, 3 plus 1, 4, 3 plus 1, 4, 4 plus 2, 6. Let's take 8 mm. So 10 mm is max width we can get, and length up to 17. So 17, 17, all 17 mm. So it would go up to 17 threes, 17 threes are 54. I think it would go to 60 mm of the length. So let's take a 16 mm, 60 mm. We'll take a 60 mm as the length and 10 mm as the width. And we will also understand how we can design this bandpass filter. First, so we'll try to give it. And so the length for this one is 17.85. One 17.85, 1.029. So this is first one. Uh, so instead of this, so I'll try to create a rectangle over here. So first height is h, and the x size is how much? It's length is 17.85 mm. 17.85 mm. So let's take is L1. Let's take, because most of the edge coupled filters are symmetrical. So if we give the variable, it would be easy for us to give it also. And y1 it is 1.029 mm. So we'll try to give it a 1 minus 1.029 mm. Now, so this is the spacing between the 0.623. So next is the next rectangle. It would be same in the length. So the next rectangle, whatever the couple line we are trying to do, I think this one, so this one we have done. And this one, if we wanted to do, we have to give the spacing between these and have the same rectangle. So the spacing is the only thing. So how can we decide the spacing? It's simple. So this is the so this is either y, it's y. So if we can minus that y from 0.18 mm minus 0.6213 mm. That's it. It should come. Okay. So it has taken from here. So we have to see from this point. So let's see what is the value of this point. It is 17.4. Okay, we have to see. It is not like that. So now we have to minus 18 the width one, and again the minus so because the 18 was from here, and we have bring down to this stage, and again 0.6213, it came here to here. So now again, see, either we can directly connect the stage, or we can use any taper transformation. So that's up to us. But I think these guys did not provide any transition. So I assume they're trying to do it simultaneously. So I'll also try to do in that same format. So this one is done. So this N1 is done. So now we'll go to the N2. So now if we wanted to go to the N2, so now we have to, so I'm trying to copy this. So we'll try to CB1, C underscore 1 underscore 1. So I'll give it 1 1 couple line underscore 1 underscore 2. And now I'll give this one as the couple line underscore 2 underscore 1. So now I give it this. So now the thing is I have to move from here to here, or I can move simply the center to center. So I simply right click edit and surface move. Where is the arrange move? Okay. come over here. Now the thing is we have to see whether there's a height change. No, 17.85 is smoother. Now I have to see the length is 17.56. So the 17.56 length did we have to change this length 17.56. So 17.56 into that is 17.56 mm, and W2 that is 1.341. 1.341 mm. So that's there. Now we got this because of the width has been more. Now it has been done. Now so as we have finished the designing this length and width, we have to go for the spacing. So spacing again is so simple. So copy this and paste it. That's C22, and I have to go there to minus this W2 and I have to do this. What is just I wanted to see the distance. So 1.762. So I have to do 0.76 mm. So the distance of this one, let's see, I think they did not change much. This is 17.85. So this is 17.85 minus W2 minus 1 point. I think it should come now. 1.62. But still, we have to see the distance. Let's see the distance here to here. It's 0.623. That's there. That's correct. And so it's hardly 1.5. So it's not the correct one. So from here, if it is the y plane, if it is so it is 17.85 minus W2 plus 1.341 minus 1 point minus 1 point minus 1.762. I think that would be correct. 14.82, and I think that should come around. Or else we can do like this. We can just see the what is the value of here, and it's minus 15.0087. So it's 15.0087 minus 1.762 mm. 1.762 mm. So okay, I have to keep that mm. So now it came, I think. Now we can see 1.762 mm. Yeah. So now the 1.762 mm it came. Now see the hedge is there or not. Now I'd like to every time I would like to see the move, because sometimes what happens, the when the move is there, we are not able to move it properly. The hedge slightly differs. Then the patch, the copper patch won't come on the top lane. So I have to check on that. So better to delete. Okay. So now again I'm trying to move this one to the right side. So edit, arrange, and move. So I'll try to move this here. Or else I try to move this. Assign, edit, arrange, move. So I've moved this one here. I'll see it again. So there is no much thing. So this C23, this is not C23. This is C3 underscore. So this I have done. So the second part also is done. So now we will go to the third part. That means 17.52 its length. So we'll give that just 17.L3. 17.52 and W3 is 1.369. W3 is 1.369 mm. Now you have this. W3 is 1.369 you have. And you have to give the spacing 2.23. So how can we give the spacing? We just copy, paste, and come over here, and you can see this one in the last line. So just figure out what is it? Minus 11.8777. So that's minus 11.8777 minus, this is 2.23, 2.23 mm. So that's there. So once again, I thought I would verify that minus 11.8777. Yeah, that's correct. Why it's 11.8777 minus 2.23. So I got this one. So the distance here between the both third copper lane is 2.23. That came. Now it's again. Now it will be easier because the symmetry comes over from now. So again, so the move option should be there. Right now I have to edit this one first. So this would be 4 underscore 1. Let's see. 4 underscore. So now I try to edit, arrange, move. So I'll try to increase it. So I'll make it 100. So that afterwards we can easily. That's why that is the advantage of giving the variables actually. We can easily change the substrate length and all those things. So now we have Now here any of these are replica. That means whatever are there in W2, we have to follow these. Okay. So I think this will be L2, W2. So that's it. L2 and W2 are done. And just see the distance over here. It's 8.3067. So 8.3067 mm minus what is the distance? It is 1.762 mm. 1.762 mm. One thing I couldn't do is I give the spacing value, but it's okay. It's better to talk and discuss. So, it's 6.42 mm. So I think it's okay. We'll see the distance between the spacing. I think it should come 1.20. Yeah, okay. So the last fifth coupled one, you have to see this one. So the fifth coupled one. So let's move this one. Edit, arrange, move. Actually, there are two variations. Mostly people, what they try to do is they try to create a junction, H plane T junction, and they try to connect between these two coupled lines. So that's there's one more possibility you can do, but doing that in HFSS is little time-taking process. But if you are trying to do it in ADS software, that makes you easy. So because you already have those constraints over there, you can just copy paste them. Now we have to put those. What do you say? So I have finished this fourth one also. So now the fast fifth one. This is 17.85. That means the L1 and L2. So just L1, W1, and this is the apply. That's it. And okay. Now I have to see what is this 5.5157. 5.5157, 0.6213, 5.5157 minus 0.6213. That is there again. So here it came. So the L1, the distance between these two. Let's see, 0.62. Yeah. So now we have created this entire structure. So let's see what is the value over here. That is 88.34. So now let's give that here 88.34. So perfectly it's done. Now again I wanted to see what is the distance from here to here. It's 2 mm. So again I wanted to see from here to here. I think it's quite little more. So I have to see how much should I reduce. That's 3 point. So it's 3 point something change. That means I have to do something on this. So I have to reduce. It's actually 3 calculator once you can see. So 3.8654 minus 2. It's 1.8654. So I have to remove little high. Uh, Again, I have to do this one. So I want to measure here again. So let's see. It's 2 mm. So now let's see again. These symmetrical on the top and it's 4 mm. So I'll minus this W to 18. So 18 mm. This would come here. So now the plane is okay. So now I'll try to unite these all. It okay. Now I've united. I have to give let's create the ground plane. So the bottom ground plane is done. Now we have created the ground plane. We have created the ground. So let's give the perfectly condition. I'm trying to give the perfecty for the both the top layer, couple planes, and the ground plane. So to ensure to check whether perfectly is done. So you can see this, and I'll take this as FR4 only. I think that's FR4, right? What was that? We created the 5 planes. Now we'll see what is that FR4. So it is there. So that's FR4 only. And perfectly we have given. So now the main thing is we have to give the excitations. So once we give right and left, change the planes. Once we change the plane, and you can see at the end, so there is this point. So don't worry about the line. Just try to connect with the one center and X size 0.3. So that means there is W1. This is all are W1 and this is minus H. So that's there. We have created one and we go to the left part. You create it over here also. Try to create over here. So how can you do that one? Simple. Try to put the marker over there. So W1. Let's see whether they are okay, correct. So now I have to give the excitation left, right, okay. So add, assign, excitation port, model port, next line, and just try to connect the excitation model lump port we are trying to do, that is the lump existence of 50 more and lump port, yeah, lump port 1 is done. And so I'll try to create the left one. Let's see. Sometimes I have to see. So that is there. Left is this one. This is left. So now I have to give the excitation port, line port, the second port, new line, and where to ensure that it is properly. Okay, so now the entire designing part is done. So let's have some coloring. Coloring is also good. So I'll try to have this one little lighter and couple planes. I'll have darker brown and all the ports. I'll try to have this red color. Ports are always good to have in red. Let's rename this as port 1. And port 2. That's port 2. Port 1 and that's port 2. And I think we have done most of the entire part. Just create the open region. See, that's 2.4 gigahertz, right? Create the open region. So I have to set up the analysis part. 2.4 gigahertz. Let's see what is the band which they have shown the plot. So it's around 1.6 to 3. So we will also try to keep in that case. It's 1.6 to 3.2. 101. To make it very faster, I'm just trying to keep it in the interpolating one. Just at the end. So let's just check whether everything is validated. Correct. So now we'll simulate and I'll show you the results. So I think the printer has done completed. So now let's see. Scan report S11, S12, S21. Very important. Let's see. Okay. Point two. Okay. The insertion loss. Which one did not come proper? S11. The input return loss did not come proper. I think there might be a slight impedance mismatch. Okay, rest to 2 came pretty good. And about the insertion loss. Okay, so the insertion loss is around 3.5. Actually, it's quite high. And whereas the rejections, so let's see how about the rejections came for them and for us. So what is bottom frequency? So for 30 dB down, they had this much. So what is this? Around 2.2 to 2. Uh, 2.4. So let's take around 20 dB down. So 30 dB down, we did not get much. So let's take Y marker and keep 30 dB down. So we got very less band. So let's say it's 20 dB down. What is the bandwidth of 20 dB down? So 2.250, 2.2. That's 250 megahertz of the bandwidth we got. 250 megahertz bandwidth. And the center frequency would be around 2.2. So 2.2 slightly came left, and for the insertion loss, I think the insertion loss came very low for them. What is the insertion loss? I think it's an arrow nearly zero. So the 3dB and the 3dB what is there? Actually, they do the bandwidth on the basis of 3dB points. So on 3dB, there's quite high bandwidth. So, but in the rejection, when there's a cut, they try to see the bandwidth. So it's 2.3 and 2. So here approximately of 380 megahertz of the bandwidth. So that is up to the range. So if you want better optimization, this thing is we have to give the proper impedance over this port and proper impedance at this port and see. That's it. So on to the next things. In the next tutorial, I'll explain how can we create a rectangular box around the edge coupled filter and how can we design the SMA connector onto the edge coupled filter and so that in the practical case what is the resonance effect happening inside a rectangular box and those things we will have in that because creating a SMA connector takes time and we have to give the wayport over there and that's again a second tutorial. So for the preliminary design, just